Hi, my name is Cody Barron, and today I'm going to be talking about Margaret Hamilton, one of the earlier contributors to the field of software engineering. In her early life, Margaret Hamilton, born in Powley, Indiana in 1936, was a child of many interests. Margaret realized in high school that she preferred abstract math more than their applied counterparts. In pursuit of this knowledge, she wound up working and eventually managing the Arcadian copper mine to save up for college in Hancock, Michigan. She attended the University of Michigan for undergrad and had planned to attend Brandeis University for grad school, but she instead found work at MIT, where her involvement in computer science began. She was eventually hired by Dr. Edward Lorenz at MIT, who needed somebody to program on his behalf. His workstation of choice was an LGP-30, and in these days, computers were programmed in literal written instruction on paper punch cards, where clusters of punched and unpunched sections represented binary instructions. She wrote weather prediction models, which at the time nobody else was notably working on because these programs often involved large-scale matrix operations. Heavily inspired by and continuing to work with Edward Lorenz, Hamilton began working at Project MAC, which was a mathematics and computation MAC research lab. Initially, the function of the project was to create a functional, time-sharing system. It was here that Hamilton would continue to program weather prediction models for her computation system, the PDP-1, which is pictured here. As prestigious as working for Edward Lorenz was, it was not a moneymaker. Having just become a mother herself, Hamilton began seeking work elsewhere and found it at the Lincoln Laboratories as a programmer on the ANFSQ-7, which was a computerized air defense command and control system pictured here. More specifically, it was the XD-1, a prototype. Initially, her duties were to reverse engineer existing code from recently departed talent, a consequence of not commenting code. Because of this experience, she informally, then formally introduced the practice of code documentation to avoid future upsets. After some time, Hamilton was then hired onto the Apollo program, where she was chosen to program the onboard systems. She was initially tasked with programming executables in the event of mission abortion during testing. This was initially an afterthought because none of the engineers considered an abort scenario to be a real possibility. Eventually, an abort does happen, and her code worked perfectly, thus cementing her position in the program. After having proven herself in unmanned testing scenarios, Hamilton transitioned into a control systems role. There, she was in charge of determining how different algorithms and pieces of software interacted with each other, since most of these functions were built independent of each other. Hamilton eventually transitioned to performing the exact same responsibilities for the Lunar Excursion Module, which was the lunar lander. Due to mistakes she made while on this project, she also conceptualized and formalized the practice of working with offline versions of code to check operability before pushing them into service. Hamilton eventually becomes the head of the software engineering department. Because software development was still a fledgling industry, software submission was an informalized and hectic process, with execution priority often being parasitic to one another. It was because of these difficulties that another responsibility of hers became deconflicting these parasitic operations to make sure that the lower priority systems wouldn't disable the higher priority ones from operation. Due to hardware limitations at the time stemming from low total memory, which is then split into persistent and erasable memory, with multiple programs trying to share that erasable memory, Hamilton's newfound responsibilities became of paramount importance. One such issue arose during simulations for the Apollo 8 mission. If astronauts erroneously selected other operation regimes during flight, the systems would crash due to them sharing erasable memory. Hamilton's solution was to introduce a message that would state that the aforementioned operations were forbidden instead of just crashing the whole op. After graduating to the Apollo 11 mission and plagued by similar worries of program confliction, Hamilton set out to create a system whereby priority emergency communications would interrupt module displays for immediate troubleshooting. This led to 5-second displays where emergency comms would interrupt for 5 seconds before seating displays back to their previous instructions. This immediately became useful as the command module experienced two such issues during landing regimes. The prioritized displays allowed for prompt fixes and issue resolution. This single specific code solution, Hamilton wrote, saved the mission and avoided probable catastrophic failure. One of Hamilton's biggest lasting impacts was her introduction of man-in-the-loop programming, which is the principal decision-making authority in use in many industries today, where the risk of human life cannot ethically be left to machine decision-making. Additionally, she formalized many of the coding practices that we take for granted today, including code documentation, error branch fail-safing, software deconfliction, and parallel program optimization. The central limitation of this project is a lack of referenceable authored work by Hamilton specifically, in part due to her not needing to publish at the time, and in part due to documentation standards of the time not meeting the digitization standards of the future. Here are some of the better references I was able to find. Please let me know if you have any questions, and I'll do what I can to answer them. Thanks for your time.